about sine is 75 degrees. Also, just using them, they'll tell you to use one of the sum and difference identities, meaning you'll have to find a couple of other values using your x squared plus y squared equals r squared technique. And now the other way that you'll see identities used, of course, is proving identities. And some of your trig identities, so we're back to proving, some of them may involve the sum difference identities, right? Not many of them. There's really not many identities we end up playing around with sum and difference. But if you see the word prove, you know, and quite often you'll be given a t-chart, so that's another giveaway, that you're proving an identity. Remember, left-hand side equals right-hand side? So all the rules we learned about solving identity or proving identities last week apply here. We work one side or the other separately. You can actually work on both sides, you just can't transfer terms. So just like before, I kind of looked at my left hand and my right hand and I decided what side am I going to start with? What's the obvious side here, left or right? The left, for sure. And then you see something weird looking, might have been weird last week, but since we've been working on sum difference, as soon as you say prove identities, you've got your identity helper sheet, right? And for most of the exam, when the exam comes, this is all you have, right? You don't have your calculator for most time. This is your one tool, your set of tools on this sheet. So obviously just have this in front of you. If there's something that stumps you, say, well, I've got a cos of an a minus b. Let's look what I got here, cos a minus b. So I would just try playing around with the formula. So it says cos of a minus b equals, so I'm going to start with my left-hand side. Here's my a, there's my b. So that's going to be equal to, according to my formula, cos of pi on 2 times cos of x. Okay, again, I'm just following the pattern. Plus sine of pi on 2 times sine of x. Okay. Quite often in identities, things get worse before they get better. And sure enough, I made something kind of that was a binomial into a larger piece now. So now what do I have? Let's see what I can do here. Notice they gave you a mix of known quantities and then unknowns. And it all has to simplify to sine x. There's going to be some canceling here, I think, or something's going to happen here. What is cos of pi on 2? Do you remember what that is? 0, right? Well, 0 times anything is going to end up being 0, right? Sine of pi on 2 is 1 times sine of x. So you can see what's happening here, right? 0 times anything is just 0. 1 times sine x, that's just going to give me sine x, right? Cos of pi by 2 is 0. Sine of pi by 2 is 1. So left-hand side equals right-hand side. That was fairly easy. Like I say, most of your identities are not going to involve the sum difference. They're kind of very limited. Lots of your identities might involve the double angles that we're going to talk about in a few minutes. Most of your identities are the regular ones that we've already seen before. The Pythagorean and the reciprocal. Okay, what about this one? Probably we could do a similar method, right? I would start with left-hand side again. There's not much on the right-hand side. Okay, take a minute and see if you can get that one started. Okay, so did you make it this far? You use the sign difference formula, right? Sine of pi, same thing's kind of happening here, right? We get a value here which is -1. Cos of x I can't do anything with. I'm going to be left with an x, but my goal has an x, yeah? Oh, 0. Yes, thank you, Neville. Same thing, right? 0 times cos of x minus cos of pi is -1. Agreed? Sine of x. So this whole term disappears. 0 times anything is 0. 2 negatives make a positive, so I'm left with my sine x. So I have my left-hand side equals my right-hand side. If you ever got an identity with one of these sum and difference, it's kind of limited with what you can do in it, and you end up with probably a lot of terms they give you with zeros and ones, so canceling goes on, right? I did say you guys could go take a break, so if you need to run out and take a break, please do, but I'm going to keep going on, and I'll give you some time at the end of class to work again. The next thing we can do, as you notice, we've been working through identities like we did before. The first thing, we just played with the identities. We used them to expand our knowledge of special angles. Then we use them to solve identities. You can also use them to solve equations, but this is a little out of place, this page. It should actually come at the end because we haven't used identities at all to solve any trig equations. We haven't even used our Pythagorean or our reciprocal. So we're going to leave this. This actually should have been at the end of the unit with our other equations. But you can see this is not an identity because it says solve and I'm given a left and a right hand side. So we're going to leave this until we finish the double angle, and then we'll look at solving all types of equations involving identities. Okay, so let's talk about the double angles. Ibby and John? Okay, the double angle identities are used when working with angles that are related to others by a multiple of 2. That's why they're called the double. So you can see the word 2 in the identities. And that's the last set of identities that we're going to talk about. And basically, that covers this whole left-hand side of your formula sheet, right? So again, once again, these were this difference formulas, or the difference identities. I think I mentioned this before. These are the sum identities, right, because you're adding 2 angles, so they're called the sum. And these last sets are called the double angle. I find them a little more useful than the sum and difference, but let's look at the double angle. Something interesting happens here. There's a sine double angle. Sine of 2 alpha, or 2 theta, or 2 beta, equals 2 sine alpha times cos alpha. So that's interesting. Cos double angle, cos double angle, cos double angle. That means there's 3 different forms that the cos double angle can take. They're all related to each other, obviously, but just the way the cos double angle formula develops, it lends itself into 3 different ways that you can record it or use it. Tan and sine only have 1 version, but cos has 3 versions, okay? But you can see how they develop. I hope you can see, because look at what they all contain. All of the coses, sine just has 2 sine times cos. What makes up the cos double angle? What are these guys called? The squares are called the Pythagorean identities, right? So you can see inside each one of the coses is sort of like it's related to the Pythagorean. So look what happens. I could think of this as, okay, so cos 2 alpha. I could use theta, alpha, beta, whatever, but I'll stick with alpha like they did, is equal to cos squared alpha minus sine squared. Okay, that's our first version. But according to the Pythagorean, sine squared is equal to 1 minus cos squared, right? So what if I just replace this sine squared with 1 minus cos squared? Well, look what happens. I get cos squared minus 1 plus cos squared. Agreed? These two are like terms. Combine them together. So I get 2 cos squared minus 1. Well, that's this guy, right? So what if I look at it again freshly. 2 cos alpha equals cos squared minus sine squared, starting with the first one they give me. What if I replace this one with 1 minus sine squared, right? So I get 1 minus sine squared minus sine squared, which is 1 minus 2 sine squareds. Okay, that's my second, right? So they're all related to each other. That's why there's 3 versions. It's kind of nice to have 3 versions because we're going to use these identities to solve other identities or use these identities to solve equations. So having 3 versions of cos can be helpful, especially when you're solving identities, right? Because you're given a left-hand side to convert to the right-hand side. Sometimes it'd probably be more advantageous to use the formula that fits your goal better, right? But there's only one version of the tan and the sine double angle, okay? So those are your double angles. So what are we going to do with them? Well, let's see. What do we have to do here? The double angles are used when working with angles that are related to other angles by a multiple of 2. Again, I've recorded the double angles right up here, so they're easy access to you if you don't have your formula sheet with you handy. Let's see what we're going to be asked to do. Just play with them first. Given that theta is in standard position, terminal arm quadrant 3, sine is equal to negative 1/3, determine the exact value of each trig ratio. Okay, we want the exact value of sine of 2 theta. Okay. That is an identity, so it's got a formula associated with it. Sine of 2 alpha is equal to 2 sine alpha cos alpha, right up here. Sine of double of any angle is equal to 2 sine of the given angle times cos of the given angle. It's going back to that same strategy over and over again that we learned with the unit circle, right? Given one of the trig ratios, find the other 5. Well, these guys are very similar, except you don't have to find all other 5. Quite often, if you're given a sine, you have to find the cos. Given the cos, you have to find the sine. So, what do I have here? Well, I have my 2. I have my sine of theta. Sine of theta is negative 1/3. I just need my cos of theta, right? Then I have my exact value. So guess what? Back to square one, right? If sine alpha is equal to negative 1/3, that means y is negative 1, r is 3, x is going to be 9 subtract 1, root 8. Okay. So, and you can just leave it as root 8. You don't have to simplify. It's up to you. So then cos would be equal to root 8 over 3, but this was quadrant 3, right? I have to remember that. So I heard Eileen say negative. Okay, and I'll put a negative here too. Okay, so then that's just negative root 8 over 3. And then I have to come up with the final answer, right? So what would I have? It'd be positive 2 roots of 8 over 9. Is anyone bothered by the root 8? Do you want to simplify that a bit more? You could if you wanted to, right? You could say or 2 times 2 root 2 over 9, or 4 root of 2 over 9, if you wanted to. Because I know some people are simplifying a lot, which is great. You could leave it like this, though, just so you know, right? You don't have to simplify radicals in this section. It's the same thing, though. So it goes back to that basic skill we learned in the first part of trig, right? If you're given a trig ratio, you can find all the other ratios. Now you kind of know why you're solving for all the other ratios, because it's helping you with all the pieces that you might need in new identities. Okay. What about What about tan 2 theta? Now, it's the same question, so we use the same info. Remember, cos is the only confusing double angle. Tan is, there's just one version, so tan double angle is 2 tan theta all over 1 minus tan squared theta. All right, so give it a go. See if you can figure out what tan theta is and then plug it into the formula correctly. Okay, does everyone get 3 over root 8 for tan? Or 3 over 2 root 2 if you wanted to, right? Whichever way. And it's positive, correct? Why is tan positive? What do I have here? So I've got x equals negative root 8, right? Y equals, 1, yes, thank you. And why is tan positive? Quadrant 3, right? Yeah. So y is negative, I guess, x is negative, so tan is positive in root 3. Okay, so I've got 1 over root 8 or 1 over root 2 and 2. Who used root 8? Who used 2 root 2? Root 8? Okay, so I'll stick with root 8. It doesn't matter. It's okay, so tan of theta is going to be equal to 1 over root 8, all divided by 1 minus 1 over root 8 squared, right? So I got 2 over root 8, all divided by 1 minus, what does this equal? 1 over 8, yeah. Tan is the hardest, I'm going to tell you right now, because tan, all your trig ratios involve ratios, right? Fractions. So with sine and cos, you're always dealing with fractions. You're multiplying or adding. With tan, you've got a fraction inside another fraction. So you're always going to have a complex fraction. So that's the difficulty about dealing with the tan double angle or the tan sum or the tan difference. Because each one of these is a fraction, right? A ratio. So then you have fractions, inside fractions. They're called complex fractions. So you have to keep pushing through, right? So what do I have here? I'm going to try and do this as efficiently as I can. Okay, 1 take away an eighth. I'm going to have 7/8, right? So then I have 2 over root 8 times 8 over 7. So I'll end up with 16 over 7 roots of 8, right? Or if you did it, you would have had 16 over 7 times 2 root 2. So you could have done a little bit of simplifying there. It would have been, the 2's would have canceled, so I would have had 8 over 7 root 2. Right? These are the same. I think it's probably simpler just to leave it like that. 16 over 7 root 8. Okay, good? So they're just finicky. Sorry, or? Oh yeah, 4 root 2 over 7, right? Eileen took it one step further, 4 over 2 root 7. No, sorry, 4 root 2 over 7, if you wanted to rationalize. All right, so we're gonna, let's just do a couple more of these, then I'm gonna assign you some homework, okay? I'll leave. Again, these end up with solving trig identities. We're gonna leave that. We're just gonna play around with double angles a little bit more. I think these are simpler to deal with because they're smaller, right, than the sum difference. The sum difference require a lot of parts to it. The double angle, usually only you're just finding either tan or cos or sine. So let's see if you can figure out what to do here. Given that angle theta is in standard position, terminal arm quadrant 4, cos is equal to 2/5. Determine the exact value of each trig ratio. I've got sine of 2 theta. Anytime you see something weird happening in the angle department, like 2 theta, go to my formula sheet, and I see sine of 2 theta is equal to 2 times sine of theta cos of theta. That's how we deal with the double angle, right? We turn it into single angles. Okay, so we're back to our x squared, y squared, r squared. So what was I given? Given cos is equal to 2/5. X is 2, r is 5. Y is the root of 25 minus 4. Okay, we're quadrant 4. So that means y is going to be negative in quadrant 4. So sine theta will be equal to y over r. So yeah, if you just remember that same skill that we learned way back. And then it's a matter of dealing with your fractions, right? Fraction work. So multiplying the numerators, multiplying the denominators, we get negative 4 roots of 21 over 25. Once again, you guys are so quiet. I'm thinking you guys are doing okay, but I don't know. Does that make sense, that one? What about this one, cos of 2 theta, double angle cos? Remember, this is the one you have 3 versions. Which version would you pick? Version 1, 2, or 3? You'd pick 1? Why 1? You've got your sine, you got your cos. Would anyone pick 3? Yeah, I think I would. Why would you pick 3, Neville? Yeah, is that you too, Rahel? Now, you can do 1, but they gave me cos, so I know there's no error there. I could have made some small little stupid error, right? Like, I do that all the time. You guys watch me every day make a silly error. So because I'm confident in this number, I think I would use the 3rd version. But you're welcome to use 1 or 2. But I would use 2 cos squared theta minus 1 for mine. That's the nice thing about the cos double angle. You got your 3 choices. So this is a perfect example of why it's nice to have the 3 versions. But if you wanted to use number 1, Eileen and John, you use number 1, and we should all get the same answer. So I have 2 times. Now cos of theta was 2/5, so I'm going to take that 2/5 and square it. Subtract 1. Remember, in BEDMAS, exponents come first, so this becomes 4/25. Then I multiply by 2. Okay, almost done, right? I'm going to have to combine these two. I'm going to need an LCD. So that's going to be, I guess I'm going to call that 25 over 25. So I have 8, take away 25. Yeah. Negative 17/25. Did you also get that, Eileen? We did good. Yeah, you'll get, I mean, if you use the right value, right, you'll get the same answer. How are the double angles for you? Okay, what about these guys? Same as we did before on those sum and difference. Write each expression as a single trig ratio. Evaluate when possible. So you've got a sine and a cos. They're saying combine these just to have either write it in terms of sines or coses or tans, I suppose. What could you do here? Sine times cos. You know what? I think I'm missing something here. I think there should be a 2 here, sorry. Because otherwise you can't even do it. So, sorry. Can you add a 2 in there? Okay, what do you see here? 2 times sine times cos. It's sine 2 theta, right? Here, for this one, theta equals pi on 3, right? So this should be equal to 2 times sine, or sorry, I'm getting all mixed up again. See, there's my errors coming again. 2, this is like 2 sine theta cos theta, right? So I'm going to put that's equal to 2 sine of double the angle, okay? So this is what they gave me, so that's going to be equal to sine double what they gave me, which will be sine of 2 pi on 3, which is equal to root 3 on 2. Now, for this one, we could actually do it the long way, right? The long way would be 2 times sine of pi on 3, which is root 3 on 2, times cos of pi on 3, which is equal to 1/2, right? And then if I did all my math, it would be 2 roots of 3 over 4, or root 3 on 2. So you're probably thinking, well, why didn't I just do it the long way? Why do I have to do it this way? It's confusing. Well, you might not be given pi on 3s, right? Maybe you'd be given pi on 5s or something like that that would simplify to something you could work out. So you could do it the long way or the short way. The short way you only have to find one value, but just remember these guys can be powerful because you might have been given something that was not possible, like not from your unit circle initially. Okay. This one doesn't look like we can evaluate it because they just left it as a generic theta. What does this one look like? 6 cos squared minus 3. What does that resemble? It kind of resembles this one, right? The cos double angle. What would you do with this one? Yeah, I think let's see if we factor the 3 out. I'll be left with 2 cos squared minus 1, right? Which would lead me to what? 2 cos squared minus 1. I guess I could say, I don't know if this is making it simple or not, I guess I could call that just cos 2 theta, right? So that's another way to write it. 6 cos squared minus 3 could be written as 3 cos 2 theta. Just playing a bit with form. It doesn't really get us anywhere. We're just kind of looking at the, this got us somewhere, right? Because we could evaluate just with one trig ratio, but this one we're just playing around. And that's where you really get to know your play. Okay, we're going to do this one last page and then we're finished up our double angles except for solving trig equations. Then I'm going to give you, I think tomorrow's going to be mostly a work class, so you can catch up on your identities, just play and have me here in class to answer questions, and maybe I'll throw some practice questions up on the board and we'll just kind of take a breather and review what we've done with identities so far before we move on to solving equations. So come prepared to work tomorrow, bring a snack, something to drink, and we'll just spend the whole class kind of playing and solving, using identities and proving them and working with these guys. So it says prove the following identities. If you look close, it doesn't look much different from what we looked at before, but you can see here that I have a double angle here, right? So my left-hand side has a double angle, my right-hand side has no double angle. So you could start with either side again, but I think the left-hand side's more complicated because the double angle. And if you think about it, you're going to take a side with double angle and get rid of double angles because my right-hand side has no double angles left. So it gives you a place to start, is what I'm saying. Okay? Now, what else do you see about here on the left-hand side? What else can you notice about the left-hand side? It's reciprocal, both reciprocals, right? And what's one of our number one rules? We like putting things in sines and coses, right? So let's do that. If we put this in terms of sines and coses, cotan is cos over sine. And what would this be? Cosecant 2x. 1 over sine 2x, right? Okay, so it gives us a starting point. But I still, and when you're writing it, now this is going to be hard for you because you're used to writing sine squared x's, but this is a big 2, right? It's as big as the x, so don't write it like a little squared symbol. It's sine 2x. What would you do next? Change this one? Yeah, because we got to get rid of that double angle, right? So then I have my cos of x over sine of x, and that would just be 1 over 2 sine of x cos of x. And you can look at your formula sheet. So now we've got a little bit of canceling, right? And you can't cancel double angles with single angles. They have to be in the same form, right? I could cancel a double with a double, but in this case, I only had a single on the top. So these guys can cancel. So sure enough, I'm left with 1 over 2 sine, this time it is squared x. Sine x times sine x is sine squared. So left-hand side equals right-hand side. Okay, take a look at B. Same thing, right? I have a much more complicated left-hand side than a right. So I think I would start on the left. And a couple of other things. You've got you've got a 1 minus cos 2x all over sine 2x. So you've got a lot of pieces here. And you also have some double angles. So take a look at your formula sheet. See what you can do to start simplifying the left-hand side. Nothing.
So I put it.
Hello. See. What did you do here? Sorry.
This one like this, right? I put it down. So go. No? No.
This you would replace with 2 sin x cos x,
No,
right? Because that's the only thing you can do. Okay. All right, let's see. You might have worked ahead a little bit. So let's see what you got for the first one. So everyone started with the left-hand side, I'm assuming, right? There's nothing I can do with the denominator. The only thing I can do with sine 2x is 2 sine x cos x. That's it. However, on the top, cos 2x can be replaced in a variety of ways, right? Again, 1, 2, 3. So the second one, this one, 1 minus 2 sine squared? Okay. Did anyone else take a different road? Why did you choose this one, Eileen? Yeah, and this is the only version, if you think about it, you're replacing cos 2x, right? So the whole expression for cos of 2x is going to be subtracted. This is the only version, I mean, you can use one of the others, it'll just take you longer, but this is the only version that will subtract the 1 out right away, right? The other version gives you another 1 in there, so the 1 subtract out, and you're left with a positive 2 sine squared x, whoops, sine squared x over 2 sine x cos x, right? Because this is the only version, once again, that just the 1 disappears, right? So 2's cancel, this sine cancels with this one, and you are left with sine over cos, which is what you have on the left or the right hand side, sine over cos, left hand side equals right hand side. Done. Did anyone take, I mean, you could have substituted it differently, which is probably you'd have to do another substitution then, and you'd still get the answer, right, or the proof. Yeah. Okay, these two, again, like I say, with the sum and difference and the double angle, they aren't as involved as our regular identities that we saw before, the reciprocals and the Pythagorean usually. And there's kind of a clear starting point, right? So again, for this one, I think you could probably do work on both sides for this one. That's what I think I might do. Did anyone else do work both sides? So for this one, I think I would maybe go to my tried and true sine and cos, right? So this is cos of x over sine of x. And I'm going to leave this sine squared because that's great. Now this guy, I have no other choice except just to call him 2 sine x cos x. Okay, so what's going to happen here? I think I've got it already, right? Cancel, cancel. 2 cos x times sine x equals 2 sine x times cos x, right? John asked me if these were the same. They are, right? Because in multiplication, order doesn't matter. What I mean is like 2 times 3 equals 3 times 2, right? They're the same. So you can just leave them like this. And you can say that left-hand side equals right-hand side. Okay, how are you finding these identities? You always have the guide right here in front of you, right, with identities. It's really nice. It sort of just gives you the blueprint. So this is an identity, left and right. This is my sine double angle, right? So what do you get over here? Sine cos minus cosine. That's one of our patterns, right? Sine cos minus cosine, that's the sine subtract. So this whole thing equals to sine of 5x minus 3x, right? Because this is my a and my b. In expanded form, in contracted form, it's just a minus b. So I get sine 2x, and that's exactly what this is equal to. I don't really think there's any other way you could do this one. I think that's about it. All right, so again, we're gonna leave page 15 because it says we're solving trig equations. We haven't even gotten to the baby trig equations yet, so we're not gonna solve anything with double angles or some difference yet. I'm gonna give you a bit more work, and then I'm gonna have sort of a summary so far assignment tomorrow for you to work on in class. And we'll do some other stuff in class too, just to kind of make sure everyone's skills are up to date. You can do number 4 on page 206. So I'll record this on the board, page 206, number 4. And then also, again, remember that the book has lots of notes for you too. If you want to read a little bit more about double angle, there's the notes about double angles. And then I'm going to get you to flip over to 208 and 209, and you can do 1 and 2. So let's just look at that before you Number 4, we saw your prove the following identities. They gave you one value that you would know and one value you wouldn't know, so you're going to end up with a little bit of theory in here and some values. I see 90 degrees, 2 pi, and 270, so I think you're going to get some zeros in there, right, to cancel things out. And then we're on to the double angle stuff. Find the exact value of the following. Now, we didn't do anything like this in class, so let's see if you can figure out what we did in class and apply that here. Without doing this one, what does that look like to you? 2 sine 75 cos 75. Does that resemble any of the formulas you saw? I think it's the sine double angle, right? Okay. So that becomes sine of double this angle, whatever that is, right? So you should be able to find the exact, it says find the exact value, so you're coming up with a numerical answer. And then the number 2 is proving. That's what we just finished doing. So prove left equals right. And it looks like there's an obvious side to start with. Maybe, maybe not. There's only 4 of those, so it's not like it's a ton of homework, but it'll keep you a little bit involved in the double angle stuff before you go. Okay, so I'll leave it there with you. So you've got the rest of the class to work on this.